We also had taken a look at our analysis of our first circuit. And what we found went something like this. We were looking at what happens if we take a battery and we connect it to our chunk of conducting material, like so. And we asked the question, for a given voltage battery described by this EMF, this curly E, what current would actually flow? We showed that one can better analyze these situations using a symbolic diagram where the battery appears as a long line and a short line, with the long line being the plus terminal of the battery and the short the minus terminal. Wires on these diagrams are indicated just by lines, which look like wires. And finally, a conducting medium that offers some resistance to the current flow we indicate with a jagged line like this. Through our analysis, we actually came directly upon the two key laws for circuit analysis that have been tied to the physics we've been discussing here all along. There's the first law, I like to call it K1. That's generally it's called Kirchhoff's current or junction law. And it says that for any junction in a circuit, any point where you have currents flowing in and out, the net flow in must match the net flow out. That's something that we studied early on in our course when we looked at our fluid flow models. Then there was K2, that's Kirchhoff's voltage or loop law, but again, I like to call it K2. And it simply says, and we'll walk ourselves through this in this particular case, it simply says that if I add up the voltages around a closed loop, I must always get zero. Now, these laws we applied basically to this simple case, or we're discovering them for ourselves. K1 in this case told us that, well, look, if I look at each junction, it just tells me that the current going through the battery must be the current going through this wire, must be the current flowing down through the resistor, must be the current flowing across the lower wire and then back into the battery. So in this case, it's a simple application. We see that all of the currents are the same. They have the same value I that we're trying to solve for. When it came to K2, we basically said, well, let's take one point in our circuit, say A, and there's two ways we could go from A to A, exploiting the path independence of this conservative electric force. If we go just from A to A just by a tiny little motion and don't really do anything, that voltage was clearly going to be zero. The other pathway is to go from A to B, and then as we have here, and then from B to C, from here to here, from C to D, which is this term, and then finally from D back to A, D to A. We then looked at each of these voltages and used what we knew about them from the chemical processes in the battery. If I'm going from the minus side to the plus side of the battery, that's a gain in voltage. It's a positive voltage. That's plus E. That's the voltage rating of the battery. When we go along this wire, we are now going along downstream, along with the flow of the current. So any voltage change is going to be negative because we're going with the flow, not against the flow. In this case, so we would choose the minus sign for that. As good form, it's always good to write both the plus and the minuses. I like to do that, and then just circle the appropriate sign just to indicate that I've actually thought through and checked that. That really helps avoid mistakes. For the case of an ideal wire, it has no resistance, so we just multiply by 0. So that's going from B to C, up along here. As we went from C to D down through the resistor, that's again an IR term. In this case, again, we're going with the flow, not against the flow. It's a downstream voltage, so it comes with a negative sign. And finally, similarly for the last wire. The wires offering no resistance, those terms simply drop out of our equation. We're left with 0 then equaling, because 0 is from up here, the EMF of the battery minus I times the resistance of the conducting material. This then was an equation we could solve nearly immediately to find the final current flowing as the total EMF of the battery divided by the resistance. One of the key lessons you see that we learn from this exercise is the fact that I always have this option to find an equation like this, where I either just go from one node immediately back to itself, or I go all the way around a loop adding up the voltage changes, so that the sum of all of the voltage changes around a closed loop must be 0, and that has been formalized then as Kirchhoff's voltage law, or K2. These two key laws will play a key role in the analysis of any circuit, as we will see as our course develops.